क्वेश्चन इधर आएंगे सर, यहाँ पर इधर से सर आप वो कर सकते हैं, अनाउंस कर सकते हैं कि मैं रेडी हूँ।
हेलो, हाँ wait, yeah, sure. Yeah, I'm in the studio. Okay, we have just started. Okay, yeah. Okay.
Oh. सर आपको इसको नहीं क्लोज करना है, ठीक है सर, हैंगआउट वाले सेक्शन को।
स्क्रीन शेयर क्यों कर रहे हैं
सर? स्क्रीन शेयर आप फिर वो करेंगे तो फिर इस पे आप जब भी करना होगा तो आप इसको बस वो कर दीजिएगा, ठीक, मैक्सिमाइज कर देंगे तो ऑटोमेटिकली वो उस पे आ जाएगा स्क्रीन पे।
अभी क्या वीडियो शेयर है या स्क्रीन?
हाँ, अभी तो वीडियो है सर, ये हट रहा है सर, तो आप यहाँ पर अभी हट जाएगा।
क्या हो रहा है? वीडियो शेयर क्यों कर रही है पूरा स्क्रीन को? बार बार रिपीट होके शेयर हो रहा है।
नहीं सर, स्लो है ना सर, इसीलिए।
स्टॉप शेयरिंग का है। अभी पहले शेयर करना बंद कर देना, सिर्फ ये कर
ठीक है
देना।
सर, हटा दे,
क्योंकि ये बहुत कुछ तो ठीक नहीं है।
स्क्रीन शेयर स्टॉप कर देना सर। बाद में सर यहाँ से शेयर कर सकते हैं आप, अगर आप कुछ भी लिखना हो तो इसको शेयर में जाके फिर उसका मैक्सिमाइज करके आप कर लीजिए।
ठीक है, क्वेश्चंस कहाँ पे आएगा
सर? इधर ही आएगा सर, आप यहीं पर इधर ही आप जो भी क्वेश्चन कर रहे हो उधर करें। नहीं सर, एक मिनट सर, इसको कुछ नहीं करना, ये तो वो है सर लाइव वाला, यहाँ आएगा सर, आपने यहाँ पर किया है ना अभी सर, ब्रॉडकास्ट वाला सर क्लोज ना करिएगा सर, इतना ठीक है कि सर इसको
बहुत नीचे और थोड़ा ऊपर। हाँ बस
ठीक है,
थोड़ा नीचे, थोड़ा नहीं ऊपर, बस
ठीक है सर। इसमें कई सारे वो खुले हैं ना सर, तो इसमें थोड़ा ध्यान से करिएगा, टैब खुलेगा। डिस्कनेक्ट तो नहीं होना चाहिए सर।
डिस्कनेक्टेड नहीं, 1 मिनट मोहित्री मैम से कुछ पूछना है, बोलो
ओके,
क्वेश्चन पेपर का पैटर्न के बारे में पूछ रहे हैं, तो 1 मिनट ये माइक है क्या?
सर नहीं, इसी में मैक है सर।
अच्छा, लाइव है ना? ठीक।
नहीं आ रहा है, सामने आना चाहिए। तो ठीक है, लाइव तो जा रहा है सर। करते हैं, स्टार्ट करते हैं इसको।
वो बीच में एक बार डिस्कनेक्ट हुआ था। हेलो। हाँ, 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 हाँ। कितना देख लिया? अच्छा, ठीक है। 2 दिन लगेगा। हाँ। ठीक है, ठीक है, ठीक।
सर एक बार वो करिए सर कि आप सुन पा रहे हैं कि नहीं सर? लेकिन इसमें ये डायरेक्ट नहीं आ रहा है ना सर? इसको इस पे नहीं आ रहा है ना सर? इस पे आना चाहिए टाइप।
वो ठीक है, वो नहीं आ रहा है तो ठीक है।
अच्छा सर आप देख लीजिए, पूछ लीजिए आप विजिबल है कि नहीं और वो सब माइक आवाज सुन पा रहे हैं कि नहीं?
Let me know if you are able to hear me and you're able to see me properly. Hello, can you hear and see me properly? Okay, so there is a question regarding the asking whether it is compulsory to obey the conditions or always for observing peaks. Now, the condition for the peak is something that has to be obeyed, because the peaks in the X-ray diffraction, they correspond to the Bragg condition, that is lambda equal to 2d sine theta. So that condition has to be observed for has to be obeyed for observing the peaks. Now, if you take in practice, if you go to a lab and you do an X-ray diffraction, okay, you will see that the peaks are not very sharp; they are actually slightly broad. Okay, and the reason is that there are lattice vibrations, okay, that makes the peak a little broader. Okay, but for all the practical purposes, at least the purposes of this course, for X-ray diffraction, you have to satisfy the condition for peaks. I hope that answers your question. Okay, there was one more question regarding the pattern of the exam. Okay, and I wanted to tell you that the exam will be a multiple choice based exam. It'll be similar to the questions that were asked in the assignment and some other general questions. And it will cover everything that that is covered in the 12 weeks of this course. Okay. So please write any other questions you have and any suggestions you have or anything you want me to discuss on the forum, that also you can write. Okay, there is a question on basic solid state chemistry books. Now, there's a classic book on solid state chemistry by A.R. West. Okay? That is solid state chemistry and its applications, which I mentioned in the introduction to this course. There is another book by Smart and Moore also on the solid state chemistry. So these are some of the classic books. But I should say that some of the topics that I have been doing may not be in these books. Okay? So I've been taking topics from different places. So if you have any specific topics and you want references for that, I have tried to give them along the way during the course. Okay, but if you want references on any specific topic, then you can ask me, and I'll be happy to give you those references. But the basic book in solid state chemistry, as we said in the beginning of the course, is a book by A.R. West called Solid State Chemistry and Its Applications. And in this course, we have not done, A.R. West, the book by A.R. West spends a lot of time on synthesis, on the different synthesis methods, and a lot of time on the characterization, several pages on discussing these things. In this course, I have focused more on the concepts related to solid state chemistry. So it is slightly different from A.R. West in that sense. However, A.R. West, especially the first few chapters, are very good to read. Okay, please type your questions or anything you want to say. Please type it, or if anything you want me to discuss, anything you want me to explain in more detail, I'll be happy to discuss. I have a tablet here, so I can write and explain things also. Okay, there is a question that asks how we can determine the crystal structure of any molecular, and I'm not sure what exactly it is meant. Do you mean a molecular material, that is a material made of molecules like anthracene crystals or naphthalene crystals, or do you mean the ionic compounds like the ones that we talked about, like the binary compounds? So let me explain. So the crystal structure, the one and only way to determine crystal structure is X-ray diffraction and X-ray crystallography. X-ray diffraction will give you the lattice parameter, and it will give you the type of the crystal, whether it is primitive, face-centered, body-centered, etc. And so if you take any ionic crystal like zinc blend, okay, then if you look at the basic diffraction pattern, the powder diffraction, okay, then you will see that you'll see various peak locations, and based on that, you can, as we have seen, we can calculate, we can tell whether it is a primitive, face-centered, or body-centered. Okay. Now, once you get the powder diffraction pattern, okay, you cannot tell the exact location of the atoms. To do that, you have to do more sophisticated techniques. In that, single crystal X-ray diffraction or X-ray crystallography is used. Okay, where you actually use the information about the atomic form factor and calculate the structure factors and calculate the various peak intensities. Now, however, this requires a much better instrument. Okay, and you need a better X-ray source, typically something like a synchrotron source. Okay, that is how you can determine the structure of any ionic compound. Okay, but so what I'll say is, for the basic structure determination, you can use powder X-ray diffraction. If you want more close look at the structure, so for example, if you take the zinc blend, if you do a powder X-ray diffraction, you will learn that it is a face-centered cubic lattice, and you'll learn what the lattice parameter is. However, within the face-centered cubic lattice, I mean, the zinc blend has a 2-atom basis, has one atom at the corner and one atom at a quarter of the diagonal. Okay, so you won't get that information, will not be available through the powder X-ray diffraction. In order to determine that, you will need to use more advanced techniques like single crystal X-ray diffraction or X-ray crystallography, or or use a more powerful source like synchrotron radiation. Okay. Now, the next question is, what is the use of a Wegener seed cell? There is a conceptual use of the Wegener seed cell, is the following: that if you take any crystal, okay, then there are several symmetries of the crystal. That means there are axes of rotation, there are reflections and glide planes, and so on. Okay, so there are mirrors, rotations, reflections, inversions, etc. So now the crystal as a whole will have all these symmetries. Now, there are several ways to choose your unit cell, but if you just take your unit cell, that might not have all those symmetries. Okay, your unit cell might not show all those symmetries. And the other thing is that as you probably have learned, like if you take an FCC, okay, for example, the unit cell, the conventional cubic unit cell, has 4 atoms. Okay, and so now if you want to make a unit cell that has only 1 atom, okay, and it has the entire symmetry of the crystal, okay, then you can use the Wegener seed cell construction. So the Wegener seed cell is another unit cell that has exactly 1 atom, and it has the entire symmetry of the crystal. Okay. Now, what is important is that the Wegener seed cell exists. So for every crystal, you can determine the Wegener seed cell. And the second point is that there is a systematic way to construct it. And so once you know that it exists, then this turns out to be very, very useful when you are doing the reciprocal space analysis, okay, as we have done in the case of the Bloch theorem. Okay, when we look at when we show the band structure, we look at a path in K space, and you need a range of wave vectors. You need a range of crystal momentums, and each of these wave vectors, each of these K values, okay, you need to take only in the first Brillouin zone, and the first Brillouin zone is the Wigner seed cell of the reciprocal lattice. Okay, so you need to know the energy versus K relation only in the first Brillouin zone, because all other zones the structure is periodic. Okay, so that is the use of the Wigner seed cell. Okay, now there is a question that asks, how can we determine HCP, CCP of any unknown molecule? Yes. So the thing is, if you, I mean, most of our X-ray diffraction, we have been looking at cubic crystals. Okay, we have been looking at crystals with a cubic symmetry. Now, in general, the X-ray diffraction also works for all other crystal systems. It's not that it only works for cubic systems. The other crystal systems have a more complicated relation between the distance between lattice planes and the lattice parameters. So the distance between the lattice planes, okay, that appears in the Bragg condition. Okay, so maybe I can just show this on the screen. So in general, you have a relation that looks like lambda equal to 2d sine theta. This is valid for all crystals. Okay, this is valid for all crystal systems. Okay, now for cubic systems, you have a relation D is equal to A divided by square root of H square plus K square plus L square. Okay, but there is a relation between D and A for all other systems. For example, for orthorhombic systems, D is you can write the relation between D and A in the following way: 1 over D square equal to H square over A1 square. Or in orthorhombic crystal, you have three lattice parameters, A, B, and C, which are different from each other, over B square plus L square over C square. So this is the relation for between D and A, B, C for a orthorhombic system. Similarly, there is a relation for even for hexagonal systems. Okay, relations exist for all systems. Okay, so there are such relations for all the crystal systems. So essentially, what you do is you, in an X-ray diffraction, you try various relations. Okay, and then you see which one works. अभी ये शेयर हो रहा है क्या?
नहीं दिख रहा हूँ अपन तो शो नहीं हो रहा सर इधर शेयर करना होगा ना
Okay, I'm sorry I didn't share the screen the last time. So here is the relation. Okay, so what I said is that for any crystal you have lambda equal to 2d sine theta. This is the Bragg condition. Okay, this is valid for all crystal systems. For cubic systems, there is a relation between the distance between lattice planes and the lattice parameter. In cubic systems, there's only one lattice parameter A, Okay, and you can write a simple relation. For orthorhombic systems, also you can write a relation. And you can also write, in the orthorhombic crystals, the relation is 1 over d square is h square over a square plus k square over b square plus l square over c square. For all other systems, you can write similar relations. Okay, and what is important is that such relations exist. So if you are trying to determine the system of a crystal, then you essentially you try relations for various systems and you see which one works best. Okay, and that's how you determine whether it is HCP or CCP or anything else. Excuse me. इसको hide करो, continue करो, share करना.
स्टॉप कर दीजिए, जब भी शेयर करना तो यहाँ से ये स्टॉप. ठीक है,
यहाँ भी शेयर करना.
स्टॉप कर दें सर.
स्टॉप मत करना. ओके, वो देखता हूँ. ओके, तो ऑडियो तो जाएगा. ऑडियो तो
वो चल रहा है सर.
Okay. The next question is there any C2 axis in diamond structure? If yes, then what is its position? And the answer is yes, there are 3 C2 axes. Okay, and these are passing through opposite phase centers. Okay, so I'll just show this. So if you go to the diamond structure, so the planar representation of the diamond structure, okay. So these are the points at z equal to 0. And then you have points at z equal to 1 by 4. You have points at z equal to 3 by 4 and z equal to half. You have points at z equal to half. So now diamond cubic. So now you can see that there is a C2 axis perpendicular to the screen, passing through this atom that I've circled in green. So there's a C2 axis. So this is a C2 axis. Okay, you can clearly see that if I rotate by 180 degrees, then this green point, okay, it moves to this green point, and since they are at this end, and then this green atom will come to this atom. Similarly, the red atoms will get swapped, and all the phase center atoms will, and the edge center atoms will also be permuted. So diamond has 3 C2 axis. Okay. Now you could actually if you have a C4 axis, okay, that implies a C2 axis. Okay, but actually diamond does not have a C4 axis. Okay, diamond does not have a C4 axis. It has a 4-bar axis. Okay, so this is not a 4. It is not a 4 axis. Okay, the same C2 axis is also a 4-bar axis. Okay, so 4-bar axis is the same as the C2 axis. It is not a 4. It is not a 4. Okay, so that is about the diamond. That is about the C2 axis in diamond. So you can also do this in the following way. You know that this is also a 4-bar. Okay. So now if you do this 4-bar operation twice, if you do 4-bar twice, Okay, then what you will get is 4 bar is rotation by 90 degrees and inversion. So if you again rotate by 90 degrees, that is like rotating by 180 degrees, and then you're again inverting, so you come back. So this is equal to a C2. 4 bar twice is a C2. So if you have a 4 bar axis, then you automatically have a C2 axis. Okay, there are a couple of more questions that have come. Yeah, so there is a question. Okay, this is regarding the question in the assignment. Okay, this has to do with the integer fractions that you get in X-ray diffraction. And the question was that this is we saw this in the assignment. Okay, so you can get HKL of or H square plus K square plus L square is equal to 1, 2, 3, 4. These might be the fractions. Okay. Now if you say the fractions are 1, 2, 3, 4, then you'll get the lattice planes as 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, and 2, 0, 0. Okay. Now this fraction is the same as, this is equivalent to having a fractions of 2, 4, 6, 8. Okay, and in this case, the lattice planes will be 1, 1, 0, 2, 0, 0, 2, 1, 1, and 2, 2, 0. Okay. Now, if you look at these, allowed values of HKL, in the first case, you will conclude that this is simple cubic. In this case, you will conclude that this is body-centered cubic because H plus K plus L is even in this case. So it appears that with the same peaks, you could fit them into either condition. Okay. So now suppose you take the second condition. Okay, and let's say this corresponds to a theta value of theta 1. Okay, let's say theta 1 is the angle corresponding to the first peak. Now if you use the Bragg condition, so you get lambda equal to 2d sine theta. Okay, and for this theta 1, okay, so if you calculate, so let me rewrite this. I'll write this as A is equal to lambda by 2 sine theta times square root of H square plus K square plus L square. So I just rearrange this a bit. Okay, because D is A divided by square root of H square plus K square plus L square for a cubic system. And so I get this relation. Okay. Now, suppose I use simple cubic. So using simple cubic, okay, and we use this and calculate A. So you will get A is equal to lambda divided by 2 sine theta 1. Okay, and using this, H square plus K square plus L square is 1. Okay, so you'll just get this. On the other hand, if you use BCC condition, you will get A is equal to lambda by 2 sine theta 1 multiplied by root 2. Okay, so what you see is that the same peaks could be fitted by using a simple cubic lattice of a smaller lattice constant or a BCC with a larger lattice constant. So in general, if you don't have any information, you cannot distinguish between these two. Okay, so you need additional information, and this is very important. You need additional information to distinguish. Okay. Now this additional information. Okay. Now it has to be specified in the problem what this additional information is. In your assignment, in the problem, I said that the lattice parameter has some value. Okay, the greater than I think it was greater than 2.5. Okay, and if you calculated using simple cubic, you got a lattice parameter that was smaller than 2.5. If you calculated using BCC, you got a lattice parameter that was larger than 2.5. But you know, one general rule of thumb is that the typical lattice parameters of materials is of a few angstroms, maybe 2 to 4 or 5 angstroms, and so you can use that to actually check whether the, I mean, if you have something like ZNS, zinc blend. Okay, now the lattice parameter is going to be quite large. Okay, and the lattice parameter that you get using simple cubic will be much smaller. Okay, or sorry, not zinc blend, cesium chloride. If you take cesium chloride, okay, you will get a lattice parameter that is quite large. Okay, but if you try to fit it in simple cubic, the lattice parameter will become too small. So you need some additional information. So in general, this has to be specified in the problem, but in general, keep in mind that A for a simple, okay, I'm using the word simple in, I'll put this in quotes. So basically, simple means not a very large crystal. Okay, simple crystal is of order, I would say 3 to or can be even less. Maybe for elements it can be of order 2 to 5. Okay, but for other crystals can be of order 2 to maybe 6 or 7 angstroms. Okay, and you can use this to help you. Okay, but you know, even sometimes even that is not enough. Okay, so in general, you need more information to identify the exact lattice. In this case of simple cubic and BCC. Okay, so I hope that ये screen को stop sharing करूँ. इसको stop करना है.
अच्छा, screen तो यहाँ से stop होगा. ठीक है, screen.
Okay, so I hope I have been able to answer the question about the correct set. Okay, and at least in the question in the assignment, you were clearly told that the lattice parameter is greater than 2.5, or I don't remember exactly what it said, but it said that the lattice parameter is greater than some number. And if you had chosen simple cubic, the calculated lattice parameter would have been lower. And so you could use that to eliminate simple cube. But in general, you are right. You need additional information. You cannot just tell based on the peaks whether it is body-centered cubic or simple cubic. Okay. Just for your information, you know, simple cubic is very rare. There is only one element that crystallizes in simple cubic, that is polonium. Of course, there are a lot of compounds that could crystallize in simple cube, okay, but simple cubic structure, but amongst the elements there is only one. So simple cubic is in general quite rare, okay, but yes, it is definitely possible in compounds. Okay, there is a concept, there's a question that asks to clarify the concepts of Miller indices of plane and directions and related problems. Okay, now let me try to do this. I'll just go on the screen and try to tell you. Okay. Okay. So let me just say a few things and then I'll show it to you on the screen. So the Miller indices, okay, these are indices that are used to specify lattice planes Okay, and in fact, the nice thing is that because a lattice is a repeating unit, so if you specify one Miller index, you not only specify this plane, but you also specify a set of parallel planes. Okay, and those parallel planes have some distance between them. Okay, now in general, you know that if I give you 3 coordinates, I can always draw a vector using those coordinates. Okay. Planes. Okay, now let me just consider a set of planes that looks like this, set of parallel planes. Okay, and these have index. Okay, so the Miller index here is denoted by HKL. नहीं किया नहीं किया मैंने नहीं किया स्टॉप है लाइव है लाइव तो है Okay. Please. Screen sharing. Okay, there seems to be some problem with the video. Okay, so we're just waiting for a few seconds. I'm just waiting for a few seconds, then the screen will be shared. Okay. Screen sharing. Okay, so now you should be able to see the screen. So I just considered this XYZ coordinates in a crystal, and I just showed these are some lattice planes. Okay, and let's say the Miller index is HKL. Now Miller index. Okay, so as we had seen, so these are related to reciprocal of intercepts on axis. Okay, so these are related to these reciprocals. Okay, so the Miller indices are related to the reciprocals of intercepts on axis. Okay, so so what you know if you have a Miller plane is that it's going to intersect each of the axes at so this intersects axis at some fraction of 1 by h, 1 by k, 1 by l. Okay, so at some fraction of that, it will intersect these axes. Okay, because when you finally, if you have intersects, from intercepts A, B, C, if you want to get the Miller index, okay, then what you do is you look at 1 by A, 1 by B, and 1 by C, and then you multiply it by the least common multiple. Okay, so you multiply by L, which is the least common multiple of ABC. Okay, so so H is the least common multiple of ABC divided by A, and so on. So now if you want to do the reverse process, then there'll always be a factor of the least common multiple that will multiply this 1 over H, 1 over K, and 1 over L. Okay. Now if I give you alternatively, you can ask, you can look at HKL as a vector. Okay, as a vector. So if you think of this as a vector, this will look like HI plus Kj. Okay, that I'm looking for a cubic crystal, LK. Okay, and I'm sorry that these two, the same unit vector is denoted by K hat, where K is the Miller index. Okay, so this is a direction. This is a vector, or it's a direction. Okay, that has a direction. And so this direction, okay, given by HKL is a vector. Okay, and so this is a this is a problem where you have to look at the geometry of the crystal. So if you take NaCl, okay, now so I'm just drawing the NaCl.
स्क्रीन शेयर हटाया था क्या?
नहीं छोटा.
ठीक है. आया. क्या लग रहा है सर? फिर से शेयर कर लीजिए.
I'm just waiting for the screen to share. There seems to be some technical problems. Okay. So if you take this as your NaCl crystal, okay, so you can take the green as chloride and blue as sodium, and this is one plane. I'm just showing one plane. Okay. Now, if you ask the sodium atoms, okay, so what is the nearest distance between sodium atoms? So this is the nearest distance between the sodium atoms. Okay, the nearest distance between a sodium and a chlorine atom is this. So this is the nearest. So this is R NaCl, this distance, and this is R NaNa. Okay, so now if you take any sodium atoms, you ask how many sodium atoms are closest to it. There are a total of 12. So there will be 4 in this plane, four in the 2 perpendicular planes, which will also be at the same distance. Similarly, for every chlorine atom, okay, you can just extend it here, and you'll get 12 chloride ions in this case, which are closest to a given chloride ion. Okay. Now, if you ask the other question, that is closest to a chloride ion, how many sodium ions are there? So if I take this chloride ion, I can see that these are all closest to it. Okay, and there will be one outside the screen and one behind the screen that will also be closer. So there are 6. So you can say that if you take a chloride ion, okay, this has 6 nearest neighbor sodium ions. 6 sodium ions that are nearest to it, closer to it than any other ion, and it has there are 12 chloride ions which are nearer than all other chloride ions. Okay, so the 6 sodium ions are nearer than any other ions to the chloride, but there are 12 chloride ions that are nearer than all the other chloride ions. Okay. So I hope this answers your question. Okay. Then there is a question. What is the concept of inverse lattice? I think the right term is reciprocal lattice. So reciprocal lattice is reciprocal lattice. Okay, so this is a concept that that we are using. Okay, it's related to the following idea, that if you have a Bravais lattice vector, so R, okay, now if you have so this looks like N1 A1 plus N2 A2 plus N3 A3. So this is your Bravais lattice translation vector. Okay. These are the unit cell vectors of the Bravais lattice. So R is in the Bravais lattice. So I say it is contained in the Bravais lattice. So this epsilon is a mathematical symbol. That means it is contained in the Bravais lattice. So it is one vector of the Bravais lattice. And N1, N2, N3 are integers. So they can go from minus infinity to plus infinity. But they have to take integer values. Okay. Now you ask a question. Okay. So suppose you look at e to the I k dot r equal to 1, and so you look for all k that satisfy this condition. Okay, so you just look for all the k that satisfy this condition. Okay. Now if you ask what are the k's that will satisfy this condition, so if this condition has to be satisfied, then it has to be true that k dot r should be an integral multiple of 2 pi n. Okay, n is an integer. Okay, so k has to be 2 pi times an integer. Okay, so all now because there are several different choices of r. Okay, there can be several different choices of k that satisfy this. Okay, so you look at the set of all k's, set of all k vectors that satisfy k dot r equal to 2 pi n for some Bravais lattice vector. Okay, so for some r contained in Bravais lattice. Okay, so what you're doing is you're asking, there can be several different k vectors. Okay, since there can be several different r's, there can be several different n values, n integers. So there can be several different k vectors that satisfy this condition. Okay, and if you take the set of all those, okay, then you will get you'll see that the set of all k's, okay, will actually you'll get several different k vectors. Okay, and now you'll get in all directions, okay, and you'll get several different k vectors that satisfy this. Okay, and if you look at all these points, okay, you'll find that they form a lattice. Okay, and this lattice formed by all these points, okay, so k vector is a vector, okay, and so it's the coordinate of a point. Okay, so if you look at all the points, okay, then they will form a lattice. This is called the reciprocal lattice. Okay, so k vector, okay, is a coordinate of a point in k space. K space is also called reciprocal space. Okay, we are just distinguishing it from real space. Okay, and this vector is this lattice that is formed by all these points is called the reciprocal lattice. Okay, so just as in Bravais lattice, we have a general lattice translation vector given by n1a plus n2b, or n1. Let me just use a slightly different notation. n1a1 plus n2a2 plus n3a3. Okay, so a1, a2, a3 are the or the primitive lattice translation vectors. So in reciprocal lattice, okay, we have general reciprocal lattice vector k is given by m1 b1. Okay, so m1 plus m2 b2 plus m3 b3. So b1, b2, b3 are the unit vectors, unit lattice translation vectors of the reciprocal lattice. Okay, so reciprocal lattice is just another lattice. Only thing it's in a different space, and there is a relation between b1, b2, b3, and a1, a2, a3. Okay, so we have the relation. So b1 is written as 2 pi a2 cross a3 divided by a1 dot a2 cross a3. Okay, so that is the relation, and similarly you have for b1 and b2. Similarly for b2 and b3. Okay, so that is the concept of the reciprocal lattice. So there's a question regarding the crystal structure of ReH2. Okay, I don't know this crystal structure, so I cannot answer that. Okay, there are many crystals whose structures are not known to me. And yeah, screen cost. Can I stop sharing the screen? Okay, so stop. So there's a question regarding the crystal structure of ReH2, and I don't know this off the top of my head. Okay, so there are several compounds whose crystal structures are not known to me. Okay, and definitely this is one structure that is not known to me. Okay, so we have actually crossed the time for this live session, but since there were interruptions, I'm willing, I can stay for some more time. So if you have any other questions, then please write it. Otherwise, we will conclude this session. So I hope I've been able to answer all the questions that you have asked. If you're still not clear, then you can write and you can ask me again, and I'll be happy to explain it again. Or if things are still not clear, you can also post it on the forum, and we will answer it. Okay. So with this, I will close this session for now. Okay. And if you have questions, then do post them on the forum. Okay? Thank you.